Then continue with chapter 16 here. Did you do part of chapter 16 in Chem 1A? That is, this part, molecular structure and acid-base behavior, and Lewis acid. What makes an acid based on the Lewis structure? Okay, we're going to do that then too. All right, so when we're looking at acids, there are two different types of questions that you're going to have with acids. You look at Ka. Ka is acid plus water. Acid plus water yields hydronium, and plus conjugate base, which is called Cp, conjugate base of the acid. We do this one step at a time. So acids will have Ka, and then there's also Kw, because when there's water around, we'll have the acid and the water. The water, Kw, also leads to hydronium plus the conjugate base. And so this is Kw, which is equal to Ka of water. And so there are two hydronium producers in an acid solution. We'll have the Ka and the Kw. Normally, Kw is a very small contributor to hydronium. So if we're looking at the total hydronium, for most problems, we only look at Ka, because Kw produces so little. The most Kw is going to produce is 10 to the minus 7 molar, max. And so the hydronium is going to be less than 10 to the minus 7 molar. Well, if the acid produces, let's say, 10 to the minus 3 or greater than, or 10 to the minus 4, even 10 to the minus 5, we probably don't worry about, And so this one, let's say, if we have greater than 10 to the minus, say, 6 molar hydronium at equilibrium from this, then we can ignore Kw. And so typically we ignore Kw, additional hydronium contribution. For additional hydronium. We don't ignore Kw for hydroxide, because all the hydroxide comes from Kw. So if we are interested in how much hydroxide is in an acid solution, then we'll need to do a Kw calculation. But if we have less than, let's say, 10 to the minus 6 molar hydronium, then what we do is Kw will be significant. So let's say we have 10 to the minus 7 molar hydronium from the acid, then Kw is going to be significant. We'll have to factor that in to it. And so there are two types of calculations that we do. One is the most common is the pH. We're just interested in pH. If we're just interested in the pH, then we want to know what the total hydronium is. If we're trying to figure out the total hydronium, then oftentimes we can skip some steps. Like, for example, here, we would skip step 2 because we'd say step 2 is negligible. For most, acid solutions, we don't work with very, very, very dilute solutions. We work with more concentrated solutions, like even 0.1 molar, which is 10 to the minus 1 molar acid. Even if it's weak, we expect it to lead to more than 10 to the minus 6 molar hydronium. And so for pH calculations, we often ignore Kw, for step 2. That saves us time, because it's not going to make much of a difference in the pH. We get a tiny bit more hydronium, but it's insignificant, it's not going to change the pH here. Or two, we calculate the inventory, that is all equilibrium species. Is all equilibrium species present. When we do this, then we have to do all the steps because we want to figure out everything in that particular solution that we do. So this is going to dictate something like this. If I have something like a triprotic acid, there are going to be 4 contributors to hydronium, like phosphoric acid. The first contributor to hydronium would be the first hydrogen breaking off, that's Ka1. Then we have Ka2, the second, and Ka3, third. There are 3 hydrogens, acidic hydrogens there. And then we have Kw. So this would be 4 steps. If we're only interested in pH, then most likely the first step is going to be the major contributor, which it should. It's 10 to the minus 3, the K. The second step is going to be like 5 orders of magnitude smaller. And so, and plus we have the common ion effect. So usually in something like this, if we want the pH for something like phosphoric acid, it's just the first step. The second step is minor contributor, third step even less, so etc. And so for something like phosphoric acid, pH, most of the time you're good with the first step. The only time you're not good with the first step is if the second step has a significant K value. And what is a significant K value? A significant K value would be like 10 to the minus 2. Let's say step 2 had a 10 to the minus, well, this is only 10 to the minus 3, but let's say this one was bigger. And your second step was a 10 to the minus 2, then that's significant. Maybe a 10 to the minus 3 K might be significant. And so these are the things that we think about when we do that. Well, how do you know these things? How you know these things is based on experience. That is, we've done a calculation and we've seen the results of that calculation. So let's do this calculation here. We're going to do both. We're going to figure out the pH and do the inventory for phosphoric acid. And we're going to just do one example in the book. So what we're going to do is we'll take a look at 3 molar phosphoric acid like they do in the book. And then we go through all the steps. This is fairly concentrated here, 3 molar. Although we'd still call it dilute. That's dilute phosphoric acid. And so phosphoric acid, what are the hydronium ion contributors to the steps Ka1, Ka2, Ka3 for phosphoric acid and Kw? And so we're looking at 4 steps here. Step 1, we take the biggest K value, which would be Ka1. The biggest K, we start off with the biggest K, H3PO4 plus water. It's going to yield hydronium plus dihydrogen phosphate. We have a Ka1 value of 7.1 times 10 minus 3. All right, so if we have a beaker that's labeled 3.0 molar phosphoric acid, what's in it? And so we've got 3.0 molar H2O is a pure liquid. This is 0, 0. So we're assuming nothing's happened yet. And then this is going to be a minus X plus X plus X. And so at equilibrium, we're going to have 3.0 minus X molar, and X molar. Okay, over here, this is going to equal the hydronium ion concentration times the dihydrogen phosphate divided by the phosphoric acid, H3PO4. And so this is going to be X squared over 3.0 minus X. So we just go ahead and try the simplifying assumption and see. I mean, there are little tests you can do to see, but the tests involve calculation or estimation as well. On the one hand, this is not so small, 10 minus 3, so we're going to get some X here. On the other hand, this is kind of big, so it could work. So we'll just try. So this is going to come out to x squared over 3.0. So we'll take 7.1 times 10 to the minus 3. 7.1 times 10 to the minus 3 times 3, and then square root that. And 0.0071. So I get an x equal 0.0071. And then we got to calculate the percent change. And the percent change is going to be the change x over 3, the initial. And so the percentage is going to be 0.0071 divided by 3.0 times 100%. You know, sometimes the change is 2x, so we'll have to multiply by 2, or 3x, we'll have to multiply by 3, but in this case it's just x divided by 3, 0.2%. So 0.2% is good. This is less than 5%. So, and it's actually pretty good. But even if we calculate using quadratic, it's not going to make that big of a difference. You know, like a 0.2% quadratic versus this, you're going to get about the same answer. Especially the number of digits we're allowed, and so I'm really worried about it. So 0.0071. So this is going to be 3.0 minus 0.0071, which is going to be 2.9929 molar. Then over here we're going to get 0.0071 molar and 0.0071 molar. All right, let's check to make sure that's okay. We're going to just calculate K, 0.0071 squared divided by 2.9929. See what that comes out. 0.0071 squared divided by 2.9929. 1.68 times 10 to the minus 5. Oops, let me do that again. 0.0071 squared divided by 2.9929. 1.68. So I get 1.68 times 10 to the minus 5. What is it supposed to be? 7.1. So obviously there's some mistake. Must have made some mistake. What's that? Oh, what did you get for your x? 0.0213. Okay, that explains that.
Well, wait, sorry.
That's also.
What did you get?
1459.
Yeah, that's right.
1459.
1459.
Yes. Okay. Let's try that again here. 0.1459.
Yes.
All right. Well, that's going to change the percentage here. And so I'm going to get 0.1459 as my change over my original 3.0 times 100%. And what did you get for your percent? Change here. 4.36%. 4.36 is not so great. You know, 4.36% is getting kind of big. And so when we have a big percent change, the simplifying assumption isn't so good. What's the limit that we're going to use? 5%. So they take this molarity here. They take this molarity so that it works. You know, if they did 1 molar here, the simplifying assumption would have failed, and we would have had to use the quadratic. Or if they pick 0.1 molar, which is what we normally do, is pick 0.100 molar, it would have failed. But when we're getting to this, you know, how hard is it, if you have a calculator, how hard is it to do the quadratic? Not that hard to do the quadratic, and you'll get a better answer. But if you just have your basic calculator, then we'll just go with this, you know. If it were me, I'd probably just do the quadratic. Simple enough. In fact, let's do the quadratic just for comparison. If I did the quadratic, I would have gotten x squared. Okay. This is going to be minus, so this is going to be plus 7.1 times 10 to the minus 3x. And then 3 times that. 3 times 7 is 21.3. Is equal to 0. Okay. And then let's just use the quadratic solver here. And I go A is 1, B is 7.1, E to the third. Bye. Square. We go with a different quadratic formula calculator. Let me try this one more time. 7.1, and that's working. Times 10 to the minus 3. And then C is 21.3.
$21.3 times 10 to the negative 3, I believe.
No, 21.3 times 10 to the negative 3. Okay, so if we just went ahead and used the quadratic without making a simplifying assumption, we would have 0.1424. So x here is 0.1424, and so this is accurate. This is just solving the math. This is with the assumption 1459. And so what kind of percent error did we just introduce into this? This isn't the percent error, this is the percent change. The percent change is just an estimate, you know, about if this simplifying assumption is good or not. It's not telling us how much error we have. The error is going to be this. And so the error is going to be 59 minus 24 divided by, it should be 24. So 59 minus 24 is 35. 35 divided by, actually, I better do that. 14 by 1424. 35 divided by 1424 times 100. 2.45% error. And so when we look at our x value, by using the simplifying assumption here, we just introduced a 2.457% error. So is that acceptable? That's acceptable, you know, 2.5% error. But if you were doing, let's say you wanted to do more accurate calculations, more precise calculations, then, and the math wasn't terribly difficult here, then I would have just done this. Especially nowadays with the calculators, this is quick, not difficult. But the book is, some of the math for sure, you know, this is acceptable versus doing a third order or fourth order or fifth order polynomial for sure. That's acceptable because otherwise the math is just way too difficult. But for something simple like a quadratic, I don't know. you know, if it really is justified to do the simplifying assumption when the math is so easy with a calculator that you're allowed to use on standardized tests. So, we do here. Which one do you want to do? Do you want to just keep going with the simplifying assumption since it's valid? Or do you want to just do the quadratic? Actually, how many?
I have a question. On the test, I know that there's some free responses. How, if we come up with something like this and we do have our calculator, how are you going to
You just, like, if you have the quadratic here,
like,
you just set up the quadratic and just show me the x.
okay,
That's it. You don't have to show me.
you know,
Basically, there are people who do the quadratic formula,
right.
you know, by hand. That's fine too. You know, there are people who like to do that.
Right, you
But
don't-
if
don't
you do
need
it
us
on,
to go through the simplifying assumption and stuff.
no, right. If you have your calculator and you do it with a quadratic or cubic equation, that's fine.
Okay.
You know, if you don't have a calculator, then just use the simplifying assumption. You know, it's fine. Unless the simplifying assumption fails, then you'll have to do some math. All right, we'll do it with the quadratic. Quadratic is going to give us a little bit. It's only because this is getting close to the limit. If this were like 0.2%, I wouldn't have bothered. You know, why do the quadratic? I mean, if it's so close, I mean, so close. Well, I shouldn't say so. So far away from the limit, then that's the case. So 0.2%, no problem. But when it starts getting higher, you know, like this, then I start to think, you know, the way things are. Okay, sorry. So I need to redo these numbers here. So we'll do it with 0.1424 instead. So this is going to be 0.1424 molar, 0.1424 molar. This is going to be 3 minus 0.1424, which will be 2.8576 molar. All right, let's check our K value to make sure it's okay. So K is going to equal this times this divided by this. 0.1424 squared divided by 2.8576. And I get 7.09 times 10 to the minus 3. Which is going to be okay. This was to 2 sig figs rounds to 7.1. So that's good. All right, now if I'm doing a pH calculation, normally you could stop here by looking at the next K value. If you look at the next K value, it's not so big. Let's take a look. It's 10 to the minus 8. Now, 10 to the minus 8 is really pretty small. If you look at that last homework problem, you hit it. And I talked about the last homework problem last night. I'll post the video. But when you have a K value of 10 to the minus 10, it's only like 0.000 triple O, so 4 O's, quadruple 0, 1% reacted. That's not much percent reaction, right? That's what the 10 to the minus, this is 10 to the minus 8, which isn't going to be much. either. But,
What's the hydrolysis, like, percentage in the regular drinking water?
regular drinking water, well, they have lots of different, ones. It depends, like bottled water or tap water, or, because bottled water, they adjust the pH to make it taste a certain way.
Filtered water?
So I think like normal mineral water is just slightly acidic, and then they have ones that are basic. The basic ones are smoother, more slippery. The bases are slippery, like soap. And so, but I'll tell you, our water here has a pH of, and I'll talk about this today. Our deionized water has a pH of about 4.5 to 5, which is pretty acidic. Why? Is it so acidic? We'll talk about that. So, but the percent hydrolysis, it depends on what's in there, And so there are different things in that. Percent hydrolysis depends on what's inside of it, what's causing the acidity. We'll talk about that. All right, so again, if I'm interested in pH, I most likely would have stopped here because this next step, I look at that 10 to the minus 8. 10 to the minus 8 is not going to be very significant. In addition to not being very significant, I have one other thing that tells me it's not going to be very significant. And so this is H2PO4 minus plus water. This is going to yield hydronium plus monohydrogen phosphate. So this will be Ka2, which is 6.3 times 10 to the minus 8. The other thing that tells me this is not going to be very significant is this. What we do is this is the common ion or common species in the problem. And so here, the hydronium, all this hydronium we're going to carry down to step 2. And so all of this is from step 1, 0.1424. So we're already starting off with a significant quantity of hydronium in there. And Le Chatelier's principle says the more product there is, it shifts the reaction to the left. If this were 0, then it would shift it to the right, because the less product there is, we shift it to the right. And so this is the common ion effect inhibits the forward reaction. We don't expect as much forward reaction. Okay, the other common species is this, the dihydrogen phosphate. So all the dihydrogen phosphate ends up here. And this is going to also be 0.1424 molar. Water is a liquid. Now, what we're going to assume is nothing's happened with the dihydrogen phosphate yet. And so this is going to be 0 molar here. And so the change here is this. We're going to have minus X molar, plus X molar, plus X molar. Okay, but the change normally wouldn't be very significant because it's 10 to the minus 8. But moreover, we already have a bunch of hydronium in here. If we have a bunch of hydronium, then we even expect even less forward reaction. And so at equilibrium, we're going to have 0.1424 minus X. Molar, 0.1424 plus X, molar and X molar. Okay, so Ka2 for this is equal to the hydronium times the monohydrogen phosphate divided by the dihydrogen phosphate concentration. And so this is going to be 0.1424 plus X times X divided by 0.1424 minus X. Here. And so automatically I just do the simplifying assumption. I do the simplifying assumption because it's so easy. And so what I'm going to get is on the top, plus X that's going to drop out. So it's going to just come out.
You just get the
Two from like a chart, right?
Yeah. Actually, this got it from here. Yeah, you can also get it from the chart. The chart is going to just call it that. So most of the time, we just use the Ka values. We don't really do any calculations because those have already been done. People have already figured out the Ka values. In the lab we did a couple of weeks ago, we actually calculated the K value for that acid based on the pH. Okay, this is going to be times x divided by 0.1424 minus x, which will just be 1.1424. And so that cancels, and then x is equal to Ka2. This is interesting. X is equal to Ka2. This is something we see frequently in this type of problem, where it drops out in step 2, which is going to equal 6.3 times 10 to the minus 8. Now, that's our change. And our initial was 0.424. So let's calculate the percent change. The percent change is our x over our initial. So it's going to be 6.3 times 10 to the minus 8 over the initial, which is 0.1424 times 100%. And so what's the percent change there? The percent change is, 6.3 times 10 to the negative 8 divided by 0.1424 times 100. So the percent change that I calculated is equal to 0.000442%. If you see a percent change like that, then here there's no use in doing the quadratic. If I did the quadratic, I'm going to essentially get the same x value here. In fact, this is how we gain experience, is let's try the quadratic and then just see what we get. And so if I wasted the time, in fact, it would be a waste of time to do the quadratic in this case. You see why? Because the percent change is so negligible. But make judgments based on experience. So let's see what our experience tells us. Here, we need to gain experience in this particular case. And so let's get this into quadratic form. So I'm going to get 6.38 times 10 minus 8 times 0.1424. So 0.1424 times 6.3 times 10 to the minus 8 equals 8.9712 times 10 to the minus 9. 8.9712. Okay, so I'm just multiplying this times that, and then minus x times that. That's going to be minus 6.3 times 10 to the minus 8x.
Multiply what by what?
This by this binomial times this. That's going to equal this. I'm going to distribute that. So this is going to be x squared. It's going to equal x squared plus 0.1424x plus 0.1424x. Okay, then I'm going to combine terms and then put it on one side. So we'll put it on that side. X squared plus 0.1424x plus this. And so what will that equal? This, okay, this is going to be plus 0.1424. This is 10 minus 8, so that's 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then a 6, 3. X. And then minus this. That's 8.9712 times 10 to the minus 9 is equal to 0. Okay, so let's see what the quadratic solver gives us for this particular one. So A is 1, B is going to be 0.142400063, 0.142400063. C is going to be negative 8.9712, e to the minus 9. So what we end up with is an x value of 6.29999 times 10 to the minus 8. What did we get? We got 6.3 times 10 to the minus 8 using the simplifying assumption. And so basically, after we do the rounding, because we can't carry this many decimal places, we're going to get the same answer. And so if your percent change is small like that, then it works out quite well. When your percent change gets kind of big, then it doesn't work out quite as well. You know? It's still acceptable compared to if you had to do some hard math. Doing the simplifying assumptions totally worth it. And so here I would have said it's a waste of time to get it in organic form because the percent change is so good. Okay. So let's go ahead and do this now, which is calculate this. So 0.1424 minus x. And so I'm just going to do that in the calculator here rather than do that here. It's going to be 0.1424 minus 6.3 times 10 minus 8. And so I end up with 0.142399, 0.1423999. Okay, I am not allowed that many digits, and I could carry it on. 837, 99937. Okay, let's add this one. This one is just going to be 0.142400063. This one is going to be 6.3 times 10 to the minus 8 molar. Okay. Did the pH change much here? And so we'll calculate the pH based on step 1. If we calculate the pH based on step 1, it's going to be 0.1424. And we'll take the log of that. The pH of this is 0.8464. So if we stopped at step 1, we would have gotten a pH of 8.46. pH 0.846. How many sig figs are we allowed? We're allowed 2 sig figs. And so we'd have to round this to 0.85. If we stopped at step 2, what would the pH have been? And so we'll take the log of this. 0.1424 00063. Okay, we would have gotten a pH of 0.846. I'd have to carry more digits to C. 84648. You know, this is pretty much going to come out the same. pH is 0.85. So do you see the step 2 here is a negligible contributor? How much did it contribute? You know, 6.3 times 10 to the negative 8 extra is negligible. And so this is why in most of the pH calculations that we do for multiprotic acid, we just do step 1. And step 3 is going to yield even less, you know, even less. And the other thing is when we're doing multi-step, this is stepwise, what do we have to check? you know. What we have to check is, we have to make sure that step 2 does not perturb step 1's equilibrium. So if the hydronium and the dihydrogen phosphate, if the hydronium and dihydrogen phosphate change significantly, then that's going to shift this equilibrium. Right? But did they change significantly? No, they didn't change significantly, so we can continue doing stepwise, because essentially, when we round this, it's going to round to 0.1424, and when we round this, it rounds to 0.1424, which is basically, didn't change much. All right, so what we're going to do, though, is we're going to figure out the inventory. And if we have to figure out the inventory for this, then we have to do all the steps. And so what we're going to do is we're just going to look at the final step here. This is going to be the final step. H3PO4 does not continue on. However, the hydronium continues on here. And the dihydrogen phosphate, this turns out to be the final step for that. And so let's double check our K value just to make sure there's no error here. And so our K value is going to be 0.1424 00063 times 6.3 times 10 to the negative 8 divided by 0.14239937. You want to carry extra digits to see or to prevent round off error. Let's see what we end up with here. 0.1424 00063 times 6.3 times 10 to the negative 8 divided by 0.142399937. We had 6.3000, etc. times 10 to the negative 8. That's good. All right. What's going to happen, though, is this hydronium and this monohydrogen phosphate are going to go to step 3. So let's take a look at step 3. Here. Step 3 involves monohydrogen phosphate and water. This is going to be the next hydronium ion contributor. It's going to contribute hydronium and phosphate. The Ka value for this is 4.2 times 10 to the minus 13. I have to be careful with the way I name this. This is Ka1 for phosphoric acid. This is Ka2 for phosphoric acid, which equals Ka for dihydrogen phosphate. So this is Ka3 for phosphoric acid, which is equal to Ka for monohydrogen phosphate. And so the 1, 2, 3 apply just to phosphoric acid, and then we look at the individual Kas if we want. So we're going to bring down the concentration of monohydrogen phosphate to 6.3 times 10 to the minus 8. that comes from the previous step. And then we're going to bring down hydronium, which is 0.14240063. So hydronium is 0.14240063. And then we're going to assume no phosphates formed yet, since there's no hydrolysis here. The change is going to be minus x plus x here, more. So at equilibrium, we're going to get 6.3 times 10 to the minus 8 minus x, or 0.14240063 plus x, and x more. Okay, so this K is equal to the hydronium times the phosphate divided by the monohydrogen phosphate. And so I'm going to get 0.14240063 plus x times x divided by 6.3 times 10 to the minus 8 minus x. Did I do that right? Okay. So what we have here is something I worry about. Like for the numerator, I think the simplifying assumption would work fine. I mean, this is 10 to the negative 13. So I have significant concentration here, and I expect the change to be very small. And so the numerator, I have high confidence that the simplifying assumption is going to work. But for the denominator, I have a much lower confidence that it's going to work. And the reason I have a much lower confidence is because I'm starting off with such a small amount. And so even if this is very small, I mean, it could be significant. Do you see that here? And so I could get fancy and say, okay, I'm just going to do the simplifying assumption for the numerator and leave the denominator alone. That's going to make the math easier. It's going to make it just a regular x, just solve for x. Or I could just go ahead and try for both, see what happens. We'll just try for both and see what happens. So if I try for both, do the simplifying assumption, I'm going to get 0.14240063x divided by 6.3 times 10 to the minus 8. And solve for x. So I'm going to get 4.2 times 10 to the minus 13. 4.2 times 10 to the minus 13 times 6.3 times 10 to the minus 8 divided by 0.14240063. Don't really have to carry that many digits. And I get an x value of 1.858 times 10 to the minus 19. Is that what you guys get?
Mm-hmm.
Okay. Well, maybe I'm wrong here because I was really worried about the denominator here. But let's calculate the percent change. In fact, you can see the percent change already. It's going to be no problem. Because the change is so small. The change is 10 to the minus 19. Our initial was 10 to the minus 8. That's 8. That's 9 orders. No, that's 11 orders of magnitude difference, which is huge. And so the percent change, we need to do the more significant. So x, this would be a more significant change in the denominator. So we do that one, 1.858 times 10 to the minus 19 divided by 6.3 times 10 to the minus 8 times 100%. And this one, you don't even have to really do it. You could just do 10 minus 19 divided by 10 minus 8 times 10 squared because it's so huge. I mean, so small. But we'll go ahead and calculate it. Divided by 6.3 times 10 to the minus 8 times 100. Well, the percent change is 3, 6, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. 2949%. Did that correctly? Would it have even been worth doing the quadratic? Not at all. You would have been wasting time doing quadratic for this one because you would have gotten just the same answer, whether you did this way or not. So it works fine. The simplifying assumption worked, and then we'll just go ahead and plug in our x here. And in this case, I'm not going to carry all these zeros. Well, maybe, I don't know. Maybe I will, just since it's the first one. This one's going to have 7 zeros and 6, 3, minus this one. Should just do it in the calculator. This is going to have 9 zeros. Three, 6, 9 zeros, 2949. Actually, no. What am I doing? This is wrong. 18 zeros. 18 zeros. 3, 6, 9, 12, 15, 18 zeros, and then 1858. So if I do this, you know what it's going to come out to, right? It's going to come out to like 0.6 zeros, 3, 6, 7 zeros, and a 6, 2, 9. How many nines am I going to get? 1, 2, 3, 4, 5, 6, 7, 8, 9 nines. 1, 2, 3, 4, 5, 6, 7, 8, 9 nines. And then an 8, 1, 42. In other words, did it really change much? I mean, if we round this, we're going to have to round it anyway. It was we call this a negligible change. Basically, it did. We did lose a little bit, but it was negligible. And did we gain much here? So this is 0.14240063 plus. Now we're going to have 18 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 1858. And so this is going to come out to 0.14240063, and then 3, 6, 9 zeros, 3, 6, 9 zeros, and 1858. And so you can see that this really didn't change either. Well, that's good, because if these two don't change, really, then does that perturb step 2? No. And so stepwise is working fine now. But x did change significantly here. X is 1.858 times 10 to the negative 19 molar. And so let's just check our calculation here. Calculate K. K will be this. Point 1424 0063. The 9 zeros, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, you know, I hit the limit of my calculator. What about you? Can you get that many digits in your calculator? No. Your calculator is going to round as well, and you have to be aware of that. So your calculator can't display a number like this. Do you know that?
Yeah, just rounded it.
Yeah, it's going to round this back to whatever, 6.3, right? And so when you do calculations You have to be aware of that. And so sometimes this is another reason to reset. The final reason to reset is because your calculator rounds the answer. And so it's because there's too many nines. If there's too many nines, it's going to round it up. And so this happens all the time. So for example, when somebody punches this out in their calculator, you know what they come out with sometimes? Like a change. Let's say you had 0.1 in the change, your calculator rounded it because it was a 0.999 or no 0.09999999, change. Your calculator is going to round it to 0.1. So you do 0.1 minus 0.1, you end up with 0. So if you have a 0 here at equilibrium and you calculate your K value, is it going to match? It's not going to match at all. And so the final reason for resetting is for calculator rounding. This used to be a bigger problem. When we had calculators that only went 8 digits, this was significant because people were getting, for their equilibrium concentrations, a 0. You can't have a 0 in your equilibrium concentration because it's going to give you a K that's either going to be 0 and not match, or a K that's infinity and not match. And so just be aware of that. If you're getting a 0, try resetting. That'll probably fix it. But anyway, going back to this. Anyway, my calculator can't carry that many, so I'm not going to bother. I'm just going to do this. In fact, I'm going overkill with the digits here. And so times 1.858 times 10 to the negative 9. I think modern calculators carry 10 digits, which is pretty good. Oops, times 10 to the negative 19. Divided by 6.3 times 10 to the negative 8. Okay, and I get 4.2 times 10 to the negative 13. This checks out 0, 0, 0. Even if I rounded those, I still got 4.2 right on. All right, this is the end of the line for phosphate. Okay. And monohydrogen phosphate. Actually, I know that we'll see it later, but the hydronium carries on. There's one final step for the hydronium, and let me do that here since I ran out of space. We're going to call this step 4. The one final step for hydronium is Kw, which is H2O liquid plus H2O liquid. This gives us hydronium plus hydroxide. And so what we're going to do is we're going to see how much additional hydronium we're going to get here. And so the initial here is going to be 0.1424 ... molar, and then the hydroxide will be 0 molar. We don't expect much here because of Kw. Kw is 1.0 times 10 to the negative 14. And that's going to equal the hydronium times the hydroxide. Your book never sets up the ice table for this. Your book just plugs it into Kw here. So what they're going to do is they're going to assume that the additional hydronium produced in this step is negligible, and they're just going to use the hydronium from the previous step here, so they don't set it up. Why? Because they're making the assumption that it should be negligible. But how do you know that without experience? They're just telling you. So we might as well do it and see. But usually I do everything the same. That way, it's a consistent pattern. So we're going to get plus X molar here. And so at equilibrium, I'm going to have 0.1424 ... plus X molar and X molar here. And then just plug that in over here. I'm going to get 0.1424 ... plus X times X. Now we're just going to go ahead with the simplifying assumption here. SA. and that's gonna simplify to 0.1424. Plus x, it'll just be 1.1424x, and then solve for x. And so x is just going to be 1 times 10 to the negative 14 divided by 0.1424, this number here. So 1 times 10 to the negative 14 divided by 0.1424. I'll try to put as many digits in my calculator as I can. 000, 63. Okay, I stopped there. 3, 6, 9. I thought this was more powerful than that. I can only fit this 3 in. That's it. Equals 7 times 10 to the. So I get 7.022. 7.02247 times 10 to the negative 14. Which would be 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's actually going to contribute more hydronium than the previous step. Yeah. And so this is going to equal, since I ran out of room here, I'm just going to write it out. 1424 000 63 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 7, 0, 2, 2, 4, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 8, 8, 5, 8. Since the calculator won't do that, we're going to do it by hand. And then the X, okay, so that's the hydronium. Did we get much additional hydronium? Not at all, negligible. And so this will be the hydronium. That's good because this will not perturb step 3. Otherwise I have to do simultaneous, which will be a bit of work. And then over here, I'm going to get 7.022 times 10 to the negative 14 molar. Okay. I'm already carrying a lot of digits, so let's go ahead and multiply this out for K, just as a double check. And so, oops, I shouldn't have cleared that. 7.022 times 10 to the negative 14. Times 0.1424. I'm just going to do that. 1 times 10 to the negative 14. 1.0000. Is that what you guys got? Yeah. So it's good. All right, so what we do for the inventory, these red ones, is we see, okay, phosphoric acid ends here. It doesn't carry on. However, hydronium carries on, and dihydrogen phosphate carries on. Then dihydrogen phosphate ends here. But hydronium carries on, and monohydrogen phosphate carries on. And then I go back over here. Monohydrogen phosphate ends here. But hydronium carries on, and phosphate ends here. And then finally, what we have is, this is it. This is cumulative total. So this is the total hydronium from steps 1, 2, 3, and 4. The biggest contributor was step 1, which gave us 0.1424, and all the others were minor contributors, 6, 3, 7.022. And then the hydroxide ends here. Well, it started here and ends here. And so if I have a beaker that's labeled 3 molar, phosphoric acid, 3.0 molar phosphoric acid. What's inside the beaker? So this is the inventory here. So this is labeled 3.0 molar phosphoric acid. And what I'm going to find inside this beaker is what's the major species? The species with the highest concentration. It turns out it's not the phosphoric acid that's the highest, or is it? Actually, it is, sorry. It's a weak acid, so this is the highest. So it's going to be 2.857. Actually, how many sig figs are we allowed? 2 sig figs. So we're going around this now. 2.9 molar H3PO4. So it's a weak acid. Weak acid is only partially hydrolyzed. We only hydrolyze 0.1 molar about. Okay, what's the next most abundant species present? So this is going to consist mostly of intact molecules. And then there's going to be a little bit of what? Okay, the next most abundant species is H2 or hydronium. It'll be hydronium. Hydronium is going to be slightly more than 0.1424 molar. But how many sig figs are we going to be allowed for that? Only 2, so it's going to be 0.14 molar. Hydronium. And then the H2PO4 minus. The H2PO4 minus is also going to be 0.14 molar, but they aren't the same. The H2PO4 minus is slightly less, and the hydronium is slightly more. And then what? Is the next most abundant species? Yeah, it looks like HPO4 is next. And that's going to be, I'll just write in scientific notation. It's going to be 6.3, essentially, I'm just going to round this. 6.3 times 10 to the 3, 6, 7, 8. 6.3 times 10 minus 8 molar. HPO4, 2 minus. Okay, then what? Hydroxide? Yep. Oddly enough, hydroxide is the next most abundant species, which is going to be 7.0 times 10 minus 14. And the least abundant species will be phosphate. So let's write that over here. And I'm going to have 1.9 times 10 minus 19 phosphate. And so, I mean, it's weird we had more hydroxide than phosphate, but that's what it is. We don't produce much phosphate. It's a minuscule amount of phosphate. So mostly in this solution, we'll have molecules of phosphoric acid, and then we'll have some hydronium present. And then we'll have some dihydrogen phosphate present. And then a tiny amount of monohydrogen phosphate, which I'm trying to write very small. And then some tiny amount of hydroxide, and a very, very tiny amount of phosphate. So something like that. The size represents how much we have. I know it's impossible to read, but just trying to show that. And then what is the pH of this? So it was the 0.1424, the log of that. Log of 0.1424, 0.846. And so the pH is going to come out to 0.85 to 2 sig figs. And we could have gotten the pH from step 1, but we could also get it from the last step here. Our calculator is not going to be able to accept this many digits. All right. So that's multi-step problem here. Let's talk about bases next, and let's see. KB, KB is base plus water. When we have base plus water, we get hydroxide in conjugate acid. So conjugate acid plus hydroxide. If I look over here, that's a Ka table. Do you see? There's a Ka, that's acid plus water. Where's my Kb table? You see Kb table? There's typically no Kb table. The reason there's no Kb table is because of the conjugate relationship. And so Kb, if there is a table, that's kind of nice. So we typically get from table of Kb's, or we have to do this. If we don't have the Kb value, we have to calculate it, or calculate using Ka for the conjugate acid, Ca, conjugate acid. So Kb is equal to Kw over Ka for the conjugate acid. And we have this relationship. The relationship is that if we have a Ka times a Kb, and these are conjugates, of one another, then that's equal to Kw. We can prove this using a generic acid and generic base. The Ka for an acid is usually hydronium times its conjugate base, which will use the generic A minus over HA, the generic acid. Kb is going to be the acid, and if they're conjugates, it'll be HA times the hydroxide concentration divided by the A minus, which would be the base. And so here we can see that when we look at Ka and Kb together, and they're conjugates, then all that's left is Kw here. And so let's take a look at some bases, base solutions here. Strong bases undergo complete hydrolysis. So let's pick a strong base like sodium amide solid. Sodium amide, the first thing we see is it's a soluble salt. Soluble salts are strong electrolytes. So if there's water around, then we expect it to split up into ions, sodium ions and amide ions, H2 minus. Now amide is a strong base. And what strong bases do is strong bases hydrolyze 100%. Strong bases hydrolyze 100%. Because strong bases are strong electrolytes. They are strong electrolytes. bases do not ionize and bases do not dissociate. Bases only hydrolyze. But they do not ionize or dissociate. So we always, whenever we have a base, we always have to do base plus water. When we have an acid, we have a choice, you know. Like over there, we're just doing dissociation rather than hydrolysis. You know? But for bases, we don't have that choice. We only can do hydrolysis. So this would be my step one. Soluble salts with strong electrolytes. This is going to have a K that's very large. And then amide is a strong base, and it hydrolyzes water 100%. And so this is going to form ammonia plus hydroxide. Kb for this is very large. How do I know? Because all strong bases have a Kb that's very large. Literally very large. Or we can calculate this. If we calculate it, Kb for this is equal to Kw divided by the Ka for what acid? The acid is going to be ammonia. Is ammonia known as a very good acid? No. Ammonia is known as a good base, but not a good acid. In fact, what is the Ka for ammonia? So if we look at Ka for ammonia, it's here, and the Ka is very small, and literally very small. And so this is going to equal Kw divided by very small. So if we have Kw divided by very small, we're going to get very large. Okay, so when we have this, then we have the same type of scenario. If I'm interested in the inventory, then I have amide and water, and so there's going to be Kb and Kw, right? Because Kw is present. Kw is always present in solutions. If I'm interested in pH, though, or the POH, the power of the hydroxide ion concentration, then do I really have to worry about Kw much? No, Kw is going to be a negligible contributor to hydroxide. And so for bases, we look at all hydroxide ion contributors, and the other base here will be Kw, which would be H2O liquid plus H2O liquid, which is going to give us hydronium and hydroxide. Now Kw is equal to Ka, which is equal to Kb, because water is kind of weird. It's both an acid and a base, amphoteric. And so when we look at this, then we look at all hydroxide ion producers in the base solution. So the hydroxide ion producers in the sodium amide solid being dissolved in water will be amide and water, Kw. Now, we do a calculation. Right? So let's say I take my sodium amide and I have 0.100 moles this, plus water. And so I'm going to make sodium amide at 0.100 molar. Okay, since I do everything the same way, we'll do it in steps if we have time. Are we out of time? 2 minutes left, okay. So for me, step one is soluble salt. soluble salts are strong electrolytes. And so I'm going to take, this is going to be aqueous. Sodium amide at 0.100 molar breaks up or ionizes or dissociates into sodium ions and amide ions. So initial, I'm going to assume nothing has ionized or dissociated, and then the change is going to be complete. And so this is minus 0.100 molar, plus 0.100 molar, plus 0.100 molar. And so at the end of this, I'm going to have no more sodium amide, and I'm just going to have 0.100 molar sodium ions and 0.100 molar amide ions. Sodium ions are neutral, right? They aren't going to do anything. And so this is the end of the line for the sodium ions. But it's not the end of the line for amide. Amide is going to continue down. And so that will be the next step, but we're out of time, I think. Actually, no, we still have a little bit of time. 7:09. And so what is the next step? The next step is, this would be step 2. Step 2 is strong base. Strong bases or strong electrolytes, or strong bases. And so whenever I have amide plus water, that reaction is complete, Kb. And so that's going to give us ammonia plus hydroxide. Okay, so the amide initial is 0.100 molar, water is pure liquid, this is 0, this is 0. The change is going to be complete. Minus 0.100 molar, plus 0.100 molar, plus 0.100 molar. And so at the end of this step, I have 0 molar, 0.100 molar, 0.100 molar. Now I told you we can't have zeros, right, in the equilibrium, but in this case we can't have zeros. Why? Because these are one way. Whenever we have very large, it's one way, so we don't have to calculate. And in fact, if we calculate Q for this, 0.100 times 0.100 divided by 0, it's infinity. Right? Well, you know, K is very large, so we'll just say, okay, close enough, basically. And so this is step 2. Step 3 is KW. And we're out of time here. So KW, we just figure out how much additional hydroxide are we going to get. What's the most hydroxide we're going to get? 10 to the minus 7. Will 10 to the minus 7 make any impact on that? No. And we're going to get a lot less because of the common ion effect. So we'll stop here and then we'll take a look at this again next time. I'm going to have, I'll have another session tonight if there's any interest, you know, for last minute questions. 10 p.m. probably.